Welcome to Maths with EJD. I'm still talking about spectral analysis. This is the fourth video on spectral analysis. And since the last video, I've been talking about data in the time domain. There we had talked about nature of signals in time domain. Here I'm looking at sampling and discretization of data in the time domain. Okay, so let's look at how this whole thing goes. Okay, first of all, I think I like to pull this heading directly above this so that by the time I turn it into a PDF document, I'll know what exactly the topic I'm dealing with is. Yeah. So that goes. So sampling and discretization. Okay, in time domain, I think that's the idea. In time domain, because we're dealing with time data in the time domain. Okay. So sampling and discretization in time domain. That, okay? Yes. So sampling and discretization in time domain. Introduction. Sampling and discretization are fundamental. In fact, I can split this up. So of course, my second video on when I was talking about using basics of Python, the second video I actually demonstrated how to navigate this whole Google Colab thing. So you want to check that out if you want to know how to use Google Colab. Okay, so sampling and discretization are fundamental in signal processing. They convert a continuous time signal x of t into a discrete time sequence xn, enabling analysis and processing using digital systems. Okay, uh, so of course we know here we're talking about discretization, right? Sampling and discretization, fundamental in digital signal processing, for instance, and they help convert a continuous time. In the last video, right, we saw the different types of signals we can have, and part of the classifications we can see is either continuous or discrete. So discretization is turning a continuous time signal into a discrete time signal x of n. So continuous time x of t, discrete time x of n, enabling analysis and processing using digital systems. Okay, so digital, right? So then we talk about the Nyquist-Shannon sampling theorem. The Nyquist-Shannon sampling theorem states that a continuous time signal x of t that is band limited, so it is limited to a maximum frequency f max, can be perfectly reconstructed from its samples if the sampling frequency f of s satisfies this formula. So the sampling frequency f of s is greater than or equal to 2 times the maximum band frequency. So when f of s is greater than or equal to 2 times 2 times maximum frequency, we can actually reconstruct the the signal, the continuous time signal. Okay, so the minimum sampling rate will be f of s equals 2 times 2 equals so f of s equals 2 times f max. That is, the maximum sampling rate is when the sampling frequency is double the maximum frequency of the band limited continuous time signal. And this is called the Nyquist rate. So the Nyquist rate is two times double maximum frequency, and the sampling interval is Ts equals 1 over Fs. That's the sampling frequency. All right. So let's talk about the sampling formula now. So don't forget, we're talking about sampling and discretization in time domain. So for the sampling formula, if x of t is sampled at t equals n times ts, t sub s, right? The discrete sequence is xn equals x times n ts, right? So, and then the ideal reconstruction will now be x of t equals summation from minus infinity to infinity of xn multiplied by sinc of t minus nts over ts, like that. That is the sampling formula. Of course, we are going to visualize all of this as we move on. And then you also have what you call the frequency domain view. So the original signal spectrum xf is limited to absolute value of f, all right? It's less than or equal to f max. And then sampling creates spectral replicas as multiples of f of s. When we started out this whole thing, we talked about sinusoids and harmonics. And when we talk about harmonics now. Some harmonics are integer multiples of some fundamental frequency, which is known as F naught. Okay, so some of these things can relate to that. So sampling creates spectral replicas at multiples of the sampling frequency. So if the sampling frequency is greater than or equal to 2 times the maximum frequency, replicas do not overlap. So we can have perfect reconstruction. But if f of s is less than 2 times the maximum frequency, the replicas will overlap, and that will cause aliasing. All right. So that takes us to the idea of aliasing and anti-aliasing filters. So first of all, talking about aliasing, when f of s, the signal frequency, right? Yeah, the sampling frequency is less than double the maximum frequency. Uh, when f of s is less than double the maximum frequency, aliasing occurs. And in that case, we have high frequency components appear as lower frequencies. And aliased frequency will now be f of a, which is equal to f minus kfs. So where k is an integer, which it's an integer, whether negative or positive integer, that's what k becomes, right? So we have an aliasing frequency in that case. We also have an anti-aliasing filter. So to prevent aliasing, so if you actually want to prevent aliasing, when the sampling frequency is less than double the maximum frequency, to prevent aliasing in that case, you have to apply a low pass filter before sampling. So for instance, you have the cutoff frequency f of c, which is less than or equal to f sub s over 2. Then you have filter transfer function, which is h of f equals, it's 1 when the absolute value of f is less than or equal to f of c, and 0 when the absolute value of f is greater than f sub c. Okay, so that's talking about anti-aliasing filter. So don't worry, we are going to have a Python visualization of all of these things beyond the math, beyond just talking the maths, right? So then we have time versus frequency resolution trade-off. Time and frequency resolution have an inverse relationship. So you have the product of time and the product of the change in time times change in frequency is always greater than or equal to half. So this is an inverse relationship because when you divide both sides by the change in frequency, so you're going to have so change in time is 1 over 2 change in frequency, and change in frequency is 1 over 2, is greater than or equal to 1 over 2 change in time. That's why they have an inverse relationship. Okay. So for an endpoint DFT, all right, so we have change in frequency is fs over n. That's sampling frequency divided by n, and then t is n over sampling frequency. So increasing frequency sample, that gives better time resolution, or which leads to worse frequency resolution, right? Better time resolution, but worse frequency resolution because there's inverse proportional inverse relationship. Then increasing n now would mean that, so if you increase this n now, so that gives you better frequency resolution and then gives you worse time localization. So you want to, it depends on what exactly you want to achieve. So you can decide to increase the sampling frequency or the end point itself. Okay, so example concept to be when you have high sampling rates, which can track rapid changes. Higher sampling rates can track rapid changes and it gives good time resolution. But long observation window, this one you need precise. So this leads to precise long observation window. That means that means you have long big value of n, right? So that gives precise frequency estimation, which is good for frequency resolution, which gives good frequency resolution. And there must be a trade-off must be chosen based on application. So whatever you're applying, so you want to decide, do you want to increase sampling frequency, sampling rate, or the observation window, which is decided by the value of n. So let's go ahead and do some Python visualization to have an idea of all the things we've been saying. For instance, let's talk about Nyquist sampling and aliasing. Okay, so for Python, Nyquist sampling and aliasing, of course, as usual, we need NumPy for numerical Python for doing some numerical calculations and doing some numerical related stuff, and then matplotlib, that's pyplot. So we have the signal parameters now. The f signal is 50, so 50 hertz. Then the time, we are working in continuous time from 0 to 0.1 divided into 1000 divisions, and the signal itself is sine 2 pi ft. Okay, 2 pi ft. But we are choosing the f to be the signal, the f signal we have, the frequency we have, which is 50. All right, so that's what we are choosing. And then talking about sampling rates, now we have a high sampling rate of 200, which is above the Nyquist value, and we have a low sampling rate, which is below the Nyquist value, right? So next, we have the sampling itself. So if you want to talk about the high sampling, then that'll be NP range. You have from 0 to 0 0.1, 1 over FS high, that's for high sampling. For low sampling, you have the actual value now, which follows the signal thing. So you have NP 2 pi FT. So the F here is the F signal we have declared up there, 50 hertz. And then the N, instead of using, so here we have used N high, here we are going to use N low, right? So, I mean, it's basically about the same. So you use the range 0 to 0 0.1, 1 over Fs high, then this is 1 over Fs low, and then the X low itself will now be 2 pi. So that's the signal in the context of whether it's low or high sampling rates like that. So we just fix them up like that. And then we do the plots, you dimension the plot here. And then for here we're going to have two subplots now. So whenever you need a subplot, you do PLT dot subplot 211. So it means you're going to have two plots, a 2 by 1 plot. So yeah, 2 rows, 1 column, or I think it's two. When the plot comes out, I'll be able to explain better, right? But we have two plots. So this is the first one now. So for the first one, we plot X against T, and that will be black. That's what this means. So the label, this is the original thing now. So we plot the X high against the N high. So the high value of the signal over against the low value, the high value of the N for the sampling, right? And then we have all these base formatting. Then we label the samples. This is for the 200 hertz sample. Okay, so that's sampling above Nyquist, which is perfect reconstruction. So if you do above Nyquist, that's normally that is Fs is greater than or equal to 2 times F max. That is perfect reconstruction because it's above the Nyquist rate. The Nyquist rate is actually Fs equals 2 F max, 2 F sub max, right? So, and then the second plot, now you're doing the low thing. So you just the same thing, you just have X against T now, be original. And then for the discrete thing now, discretization has occurred here now. So you have BSF math samples for 60 hertz, which is sampling below Nyquist, which leads to aliasing, right? And then you just run this. Of course, this plot type layout and plot show. This show helps us to actually visualize the graph itself. So if I run that now, if you look up there, you see that it's running. So once it finishes running, we can see the results. So this is the result right here. So you see the first one here shows us the sampling above Nyquist, so this is actually perfect reconstruction now. So the original thing now, so the original signal is what we have right here. But after we discretize, after the reconstruction for 200 hertz samples, so that's why we now have all these, and we know for discrete things, like we actually have specific time points. That's what you have here. But then if you sample below the Nyquist, you can see that it's so for here now, this one is happening at the ends. So you have this come here, come at very logical points. But here now, this is just all over the place. You have this here, you have this here, you have this here. It's not following the same thing because we have aliasing taking place because we are sampling below the Nyquist rates, right? So that's what that shows us right there for Nyquist sampling and aliasing. Then we can go on to look at, so we can even make this interactive, right? This can be interactive and it gets more interesting with this. So here now, we want to be able to slide the values to see the differences. Okay, let me zoom out first so we can see the things line by line before we run the code. So we want to do interactive sampling and resolution visualization. So so in this case now, we need NumPy, we need Matplotlib, and then we now need widgets. So the widgets will help us to get the sliders, float slider, integer slider, and all of that. And then we also get some kind of interaction. So again, we are using the same 50 hertz, the line space is 0 0.01, then to continuous value is 2 pi ft, So, but, because we discretized the other time, this t that was continuous now becomes like the number of divisions, the number of discrete values now. So then here now we are doing a Python, we do a Python function definition, right? So when you define a Python function, you use def, so you define is a Python function called plot sampling. So with frequency 200 for the first one here, and then we take an n, which is 128. So that's like 128 observation window. So here, Fs is sampling frequency, N is DFT length, that's frequency resolution. And then we have the sampled signal. So we have NP, a range from 0 to 0.11. That's 1 over Fs, whatever the sampling frequency we have chosen. So X sampled is now for the signal itself. So for the sampling, now we now fix the value. So the F signal that was given, and then the N, that's the small n. Where's that now? Oh yeah, the N is here now, based on what we have here. Okay. And then we have the frequency resolution, which is XFFT, and that's so you get this FFT. Okay, I think we can get some information from it. That's discrete Fourier transform, right? So, and we get it from NumPy. So we get FFT from NumPy and sampled based on the X sampled and N value that was supplied. And then the F now is the FFT together with the frequency and all that. So, and then we get a time domain plot. So the time domain plot is the first thing we have here because we're plotting the continuous value against the continuous time. That's the original thing we have, right? That's the original signal. But when we come to the frequency domain plot, then we have a bit of so here you are plotting. So in the frequency domain plot now you have f of everything up to n front slide 2, that's integer division, right? Because we're dealing with just the whole numbers. So n double front slash 2 simply means if you have 11 over 2, you just pick the 5. You don't care about the fraction over it. If you follow my playlist on Python Python basics, you understand this whole floor division, or it's also called integer division. So I think it's going to be in green. This is what this G implies rather. This B means black and this G means green. Or we can even write it out in full if you like. So in this case, you have the base formatting just empty, and then you have the label for the Fourier transform like that. So, and that is with the N that was declared. So because we want something interactive now, after you show the plot, you now need sliders. So you can slide from values. The value is 200 minimum, from 20, minimum 20, maximum 500. Step is 5. Description is sampling frequency and the N. So, we can vary f of s, the sampling frequency, and we can also vary the value of n, which we know to be the DFT length. Like we saw before, that's yeah, okay. I think coming here we saw it's discrete Fourier transform. So you see Fourier is playing out in this whole thing. So the SciPy module, SciPy.ft is a more comprehensive superset. But for now, I think we're using NumPy. So, or NumPy FFT, which includes only a basic set of routines. So if you need to use SciPy, we'll go there. So if you run this one now, using the play button. So if you run this now, we get the results. So the results here. So this is the basic thing. So this is what is happening in the time domain. I wish I can shrink this better, but this is the minimum shrinking I can do here. What else can I do? Yeah. So, okay, I think I can just slide. So this is, so for 200 hertz and 128 observation windows, this is exactly what we have. So it's looking really beautiful, right? So what I'm going to do is, let me take everything to the edge. So if the sampling is 20, that's the minimum value, and the DFT point is 32. See what happens. In the time domain, we have that sinusoidal kind of thing. And then here we just have those bars going like that, right? So let me take them to the middle. So you have, so the maximum is 500. Let me take it to 250. So if I take it to 250, yeah, and then this is the maximum here is 1024. So let me take it to 512. 512. Okay, see what it looks like. So see what you have here. All right. So you have some 2 in between for the time domain up here. And then in the frequency domain, you have, you have this very sharp peak at some point between 40 and 60 hertz. Okay. Let me take them both. Let me take the first one to the fullest sampling and take this one to the smallest. Okay, see what happens here. Okay, it still affects the frequency domain here. It's still looking this way. So what if I switch it over? I bring this here and then I bring this here. Okay, so here we have this, and this whole thing looks just like a rectangle. Okay, of course, the other thing I can do is to put the two at the ends. Okay, so see, everything becomes fully grown like this. So, I mean, so with this interactive thing, you can just keep changing what you see. Okay, but let's put it somewhere in the middle and we have this. Okay, so with this, we come to the summary side of things, where we see that we're talking about um, we're talking about sampling and discretization in time domain. Okay, so for sampling and discretization in time domain, we have, in summary, we have the Nyquist-Shannon theorem, which tells us that the sampling frequency should be greater than or equal to uh, double the maximum frequency so that you can, for perfect reconstruction. But aliasing occurs if the sampling frequency uh, is less than double the maximum frequency, So in that case, aliasing occurs. Then if you want to filter, if you want an anti-aliasing filter, so you can have a low pass filter such that f of s is less than or equal to f of s divided by 2, and then you can have time versus frequency resolution, where time and frequency are inversely related. So the change in time multiplied by the change in frequency is greater than or equal to half. And then you have the frequency resolution in terms of DFT, which tells you that the change in frequency is equal to sampling frequency divided by the sampling window. That's the DFT, the resolution, right? So with this, we come to the end of this interesting video on sampling and discretization in time domain. All right. So let me know how helpful this video is for you. And if there's something you'd like me to try out, feel free to let me know in the comments, either on Facebook or on YouTube. Till I come. Okay, well, of course, don't forget to subscribe if you haven't done that already. If you have subscribed, thank you so much. If you haven't subscribed, please go ahead and subscribe because you don't want to miss the things going on this channel. So feel free to subscribe, hit the notification bell also so you can always get alerted each time a new video is released. You can even take it a step further and become a member of the channel. Just click on join. As you get to my channel, you click see join, and there are 3 levels of membership there, and that gives you some special privileges like getting PDF copies of some of my topics I've taught on request. And of course, you can also have one-on-one interaction with me depending on your level of membership. So ultimately, don't forget to like, share, comment so that more people can have access to the great content I have going here. Till I come your way again, keep doing data, maths, and all these things right. Even Python, right? Bye.